Thank you. So yeah, the name of my talk is Modern Shrink Wrap Software, and the kind of goal I have is to share the experiences we've had at Operable on our journey of packaging up Cog, our product, for easy consumption by our users and community. It really largely mirrors a lot of what we've talked about so far, kind of starting with operating system packaging and kind of progressing through where we are today. Then I'm going to take a slightly more technical kind of detour and talk a little bit about how we're using that same technology to build a plugin API for our product. So for folks that know anything about ChatOps, ChatOps is really only as good as the commands you can build for it. And so that means that any kind of ChatOps bot or platform that you build really is only as good as its plugin API. And so we've made some kind of interesting decisions there that seem to really resonate with our community. And so I'll be talking about that in the second half. But first, a little bit about myself. So I've got a little over 20 years as a software developer. If I could grow a beard, I guess that would mean I'm a gray beard, but I can't. Whenever I do try to, it looks like I've got a bad case of facial mange, so I don't even try. For a large part, my career has been focused on infrastructure and systems management. I've worked at places like Red Hat, where I worked on the Red Hat network. I spent some time at Basho working on the query engine for the Riak distributed database. And I was VP of engineering at Chef Software, where we rebuilt the Chef server, and Facebook had the big deploy, and that was news a few years ago. And I'm also a functional programming enthusiast. Thank you. Thank you. So Cog is written in OCaml. No, I'm kidding. Yeah. No, so Cog is actually written in Elixir. I'm actually a fairly big fan of Erlang and the VM and the whole ecosystem. I'm not going to spend a lot of time on the product or kind of the technology choices around it. If you want to hear more about it, I'm happy to go on at length, like off to the side, but I don't want to turn this into some sort of shill talk about the company or our product. So when I think of kind of the ecosystem we exist in, I really think of it as kind of consisting of a few different pillars. So there's infrastructure, which is the cloud providers, Amazon, Microsoft Azure, GCP, OpenStack, Cloud Foundry. It's also kind of the foundational data stores that you use in an online app like Postgres or Redis or Mongo if you don't enjoy life very much. And then the applications, which is where most of us live for our day job. I didn't put anything in here because this is kind of whatever your business is based on. So this is largely your business concerns. And then there's automation and management. And for the folks who are slightly more old school, Chef and Puppet would fall into this realm. I'd also consider like Kubernetes and Mesosphere to be kind of in the same category. But across all of this is something I think of as human factors. And this is what I'm actually really passionate about. I think because the technical community is so technical and so analytical, we a lot of times lose sight of the humans that are in the loop with all of these different categories of applications. And it's important to think about this. And this is really why myself and my co-founder, Mark, this is why we built Cog. So Cog is a ChatOps platform. We call it a platform, and it's not really a bot because it looks like a bot when you're interacting with it in chat, as you would expect from a ChatOps thing, but it's a lot more than that. It has a Unix-inspired shared automation shell. So for folks who are familiar with Unix, you can pipe commands into other commands. You can do output redirection. So you can run a sequence of commands and send the output to another chat room or several other chat rooms or to chat rooms and a direct message, all kinds of stuff like that. And it's packaged primarily as Docker images. And our plugin API is built on top of Docker. And really, these last 2 points are the ones I'm actually going to focus on for this talk. So let's talk about Docker. So Docker's big innovation, these are all my personal opinion, is not containers. They are really nice, though, and they're incredibly useful, but it's not Docker's core innovation. And Docker's big innovation isn't really about easy deployments either. Really, these easy deployments are the byproduct of their central innovation. So you might be asking, what is their central innovation? I think Docker's big innovation is Docker images. And another way to think of them is as executable packages. So images are self-contained. They're executable, obviously. And they're inspectable and testable. And what I mean by inspectable and testable here is that you can mount a Docker image and inspect its internal file system, see what's installed. You can run it interactively and poke at it to debug things. You can look at the Docker file that built the image and understand how that image was constructed. And arguably, they're cross-platform. And for that support, I will look to, does anyone know who this is? It's Henry Ford. So, as he once said, so what to me is interesting here is that Linux, it kind of runs everywhere. And if you look at Docker for OS X, and the same thing I believe with Docker for Windows, it's still running Linux under the covers. They're just running it inside of a virtual guest, so either on like Hyper-V or VMKit. So from the user's point of view, they don't really care that it's running inside a virtual machine. What they know is that I'm on my laptop and I can run your stuff just as easily as if I deployed it into production. So it really lowers the barrier to the kind of curious experimentation and trying things out stage, which is super important when you're trying to get people interested in what you're building. So shipping Docker images. We did not start here. When we did our first release of COG back this time last year, we released some debs. Can't remember if we did RPMs or not. And we did source code tarball, and we did a couple of Docker images. Far and away, the Docker images were downloaded vastly more than the other 2 artifacts put together. So we continued that for a couple of releases, and it became super obvious to us that the Docker images is where all the interest lay. Jet lag. So we continued to release the source code tarball because we feel like that's an important thing to do. We're Apache 2 licensed. But we've stopped building operating system packages. We don't build those anymore. What we do build is Docker images. And we've changed our entire build and CI pipeline to serve that purpose. So there are some benefits to running or to using Docker images as your primary shipping artifact. So you have full control over the entire environment. So as the previous speaker was mentioning, you get into situations with operating system packages where you need to install this dependency so you can install the package you really care about, but oh wait, you're on Ubuntu 14.04 and they don't have that version of this library and this repo, and just go jump off a bridge, like life is horrible. On the other hand, what you don't have is easy ways to patch vulnerabilities, and I know this came up also in the Q&A session. And so what we feel is, since we have full control over the environment, it's kind of incumbent on us as the vendor to stay on top of CVEs that get announced and make sure that we're releasing things kind of on a timely basis so that users have the opportunity to upgrade and protect themselves from those vulnerabilities. It also gives us standardized configuration. So when you, or if you, adopt this approach, what you wind up having to do is kind of getting away from config files almost entirely. And for reasons I'll get into in a minute. The direction that we found to be most productive is, how many folks here are familiar with the Heroku 12-factor app concept? Yeah, most people are. That's the direction you really wind up heading in. So for our product, all of the configuration can largely be done through environment variables. And you don't really have to explain environment variables to anyone. Most folks already know what environment variables are, so you don't have to try to explain config file syntax or invent a config file syntax or deal with YAML or JSON or any of that. And images are easily extendable to clustered environments like Kubernetes and Swarm. These aren't configurations that we support out of the box currently with our builds, but these are configurations that we're definitely looking into shipping soon. And it won't be hard because we already have the images. And so supporting these environments is really just about exposing, some more config. And this also gives us simplified support and debugging. Kind of going back to the first point, when you have full control over the environment, you know exactly how your software is supposed to run. You know exactly how it's supposed to behave because you've specified basically everything. So we use Alpine Linux as a basis for our images. And the stock base image for Alpine Linux is 5 megs. Complete build of our product, the image is 122 megs. So we lay in our source code, the compiled source code, all of the native libraries we need in order to build and ship. But it's all there in one place. And you can look in the Docker file and see exactly how we built that, which is really nice. So it gives us easier support. And for debugging, what's really nice about Docker images is that, how many people here have used Docker very much? OK. So Docker run-it. So being able to run an image interactively and open up a shell prompt inside that image and poke around is invaluable, especially when users are running into problems in the field that you can't reproduce locally. And 99% of the time, it's DNS. It's almost always DNS. So when you want to go this approach, a few things you have to kind of incorporate into your app design. So like I mentioned, environment variables, not files. Same defaults are really, really important here. The expectation that's grown up in the Docker using community is that you can just start an image up, and by and large, it will do something useful for you. It might not expose the full functionality, but you should be able to get the basics working without having to twiddle a lot of knobs. And so this makes sane defaults super, super important. Directory mounts for user customization. So as an example with our product, we write audit logs that keep track of what every user does whenever they're interacting with our product. And that's state that you would not want to have go away if you have to restart the Docker container, which is what would happen if you wrote the files inside the container. So we expose the path to the audit logs as an environment variable, and we allow the user to specify something different. And we also give them an easy way to say, hey, I want to mount this directory when I start up your product. That way, they can mount a host directory into the container, and that data will persist across container restarts. So they'd never lose that data, but they're fully in control of it too. The default is they will lose the data, but that's probably OK, because if they're not caring about this, they're very likely in the kind of exploratory curious stage, and that's where you really just want things to just work so they can start interacting with your product and kind of wrap their head around what it does. All of this has forced us to be very mindful about how and where we manage application state. So with the exception of items like the audit log and the app logs, all of our state really lives in the database. Like, we don't scribble any other files on the file system because we know it's all going to go away. This is really not all, hopefully that's not that new of a concept to most folks. You kind of have to adopt a similar approach if you're running, say, on EC2 guests, because the default file systems are ephemeral there as well. So that's some of the characteristics you have to keep in mind. So I want to talk a little bit about how this impacts our release process. So we version all of our Docker artifacts with the code that it manages. So this means the Docker files, the Docker ignore files, the Docker compose YAML, all of that gets versioned right along with the code that it manages. So you've got a nice, kind of audit trail through, in our case, our GitHub commit history to see just how the code has changed and how we've had to update the config to work with the code. And so when you go to release something, you have a fairly high certainty that this stuff is just going to work. Eat your dog food. So everyone familiar with this phrase, dog fooding? Yeah? OK. So we do everything in Docker. We do development, we do unit and functional testing, and we definitely do integration testing, all inside Docker containers. We really don't do any we don't run anything natively on our laptops for the most part. This forces us to hit all the rough edges in our kind of Docker stuff way earlier than a user will, and heavily incents us to kind of knock down those rough edges so that the user has the best experience possible. This is huge. So I don't know about anyone else, but my personal experience with integration tests has traditionally been writing the tests is never the hard part. Getting the environment up so you can test it is the hard part. Followed shortly by the religious wars over whether or not you mock out components or you actually run the real thing, which, well, I'm a big proponent of you run the thing that you're going to ship so that you're actually testing the system as the user's going to interact with it, not some sort of kind of alternate parallel universe version where you've tried to mock things out to the best of your ability. And also as startups, you have enough to do already. Why bite off more work by trying to mock Postgres? That just makes no sense to me at all. So standing up environments with Docker Compose, dead simple. So we can easily, as an example of how this flow works, when a developer wants to merge a feature branch, they submit a PR, our CI will pick this up, run the code, build and run the code based on the Docker config that's in that branch, and run all the tests, using Docker and Docker Compose. And so by the time it gets to the end, if all the tests pass, we have fairly high certainty that that code is actually, pretty good and is safe to merge. Finally, so on the right here, this is a snapshot of our Docker Hub repo I took yesterday. So this is the primary way our users consume our releases right now. We tag all of our images with a semantic version. So you can see 0.16.1, RC1, 2, beta 1, beta 2, 1.0, beta 1. We also follow the Docker convention of using latest as kind of like a symlink tag that always points to the most recent stable release. So if users are really interested in trying out the latest and greatest, they don't have to know the version. They can just say docker pull, cog:/latest, and they're good to go. A thing we learned that seems so obvious in retrospect. So since Docker images are the primary shipping artifact we have, they're also the primary output of our CI pipelines. So for a while, we just pointed CI at our Docker Hub repo and it's like, hey, this is great. And then we looked in our repo, and we had hundreds of images. And some of them were nicely named and versioned, and some of them just had date timestamps on them, and it was a complete usability train wreck. So we created a separate repo, hub repo, just for our CI images, and those get garbage collected every couple of days with a little cron job. But we keep those two separate We have some tooling that makes it easy to promote an image from our CI repo to the prod repo, but we do that, again, keeping the user's kind of experience in mind and making it really easy for them to understand, like, what's the version history here, which version am I interested in, and it doesn't pollute it with any kind of the behind-the-scenes sausage making. All of this is in service of a really simple installation process. So for our users, they need to have Docker installed, and they need to download this Docker Compose YAML file, edit some environment variables, and then run Docker Compose up. And that's it. And to prove it, I'm going to tempt the demo gods. Let's see. Yeah, there we go. Yay. Yay, ZSH and command history. So I have to set one environment variable so it knows what IP address to use. So it's created a Postgres container. It's going to create a container to run our product. Oh, please don't tell me that it removed the image and it's got to download it. That'll be fun on conference Wi-Fi. I never should have said Docker Compose down. Yay. Oh, Mr. Murphy, I love you so much. Well, I'll let that run in the background. We'll come back to it. I hope that that wasn't going to be quite so slow. So this is for open source users. We also have kind of a enterprise, on-site, or on-prem SaaS version. And for that, we're also able to reuse our Docker images. And for any folks that are ever interested in doing this kind of thing, I can highly, highly recommend checking out a product called Replicated. Replicated wraps your Docker images in a nice kind of click-through installer that you can script to set up, nice user prompts. It comes off looking very polished. It also manages all the licensing and upgrades and all that kind of stuff for you. But again, this reuses all the work we've done to get Docker images working as our primary shipping artifact, which is nice. So doing this was just an incremental bit more work building on top of what we already had. Let me see. Oh, yay. Network timeout. Yes. Blah, 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 blah. All right, well. So before I go into the next part, any questions about any of this stuff I've talked about with Docker images? Once, twice? All right. So Docker as a plugin API. When we start going down this route of building Docker images, we at the same time, we're also building out this command and plugin API for our product. And we immediately ran into a few issues. And for folks that have ever designed a plugin API, I'm sure some of these will sound familiar to you. Installation. Where does the plugin API live, or the plugin code live before it gets installed? How does it get installed? How do you know that the user is installing what they think they're installing, that they're not being like man-in-the-middled or something? How do you do upgrades? How do you configure the plugin? How do you uninstall the plugin? I mean, it just goes on and on, right? How do you run the code that's in the plugin? Like, do you want it to execute in the same process space as your main app? Or do you want it to run off in a segregated process where you have some control over what it can see and do? There really are no right or wrong answers here. These are, whenever you're designing an API like this, it's kind of an individual case-by-case thing, but these are all things you have to take into consideration. So for us, we looked at all this and we're like, Docker solves a lot of these problems for us. So installation. Well, you can just pull an image from a repo. Upgrades. You can compare image tags and pull the image if you've got an older version and restart the container. You can query the repo to find out what set of tags belong to a repo. And so as long as you're following some sort of sane semantic versioning scheme, it becomes pretty easy to reason about, I have version X, Y is available as Y newer or older than what I currently have. Configuration. Environment variables strike again. This is another place where kind of the 12-factor design really, really works out well. And uninstallation, also simple. So remove the image, or kill the container process, remove the image, and you're done. So Docker exposes primitives that do all of these things. You're probably most familiar using them through the Docker command line tool, but that's not what we did, mostly for reasons of performance, which I'll get into in a minute. And then execution. Start a container process. And Docker exposes some knobs so that you can exert some control over what that process can see and do, so you can start making some guarantees about the capabilities of the code that's running inside that process. So how it works in practice. So this is our mascot, Cog, and this is Docker, obviously. So what I'm going to walk through is how Cog talks to Docker to execute one of these processes in a container. Now, to do this, we didn't use the Docker CLI tool. We thought about it at first because that would have been dead simple. You could just shell out and call Docker a bunch of times. It's also hideously unperformant and not a thing we knew we wanted to do in the long term. So the real upside to Docker being open source is that we just went and grabbed the code to the Docker client lib, the official client lib in Go. And we looked at, OK, when I say Docker run and an image name, what is actually happening behind the scenes? And it's not that hard. It's not that hard a process to follow. And so what we wound up doing was, in a way, writing our own Docker client that talks directly to these APIs exposed by the Docker daemon through their REST API. So we say, run this command runner script using, here's the image that the user has installed, and here's this little shim image that we've added. So one thing that's really interesting about Docker is it allows you to compose images kind of at runtime. So you can mount an overlay image on top of a base image, which is how we're able to ensure that this command runner program is always available regardless of the image that the user gives us. And the user doesn't have to care or know anything about this command runner. So we can have a sane interface that's stable for us to program against, and we don't have to bother the user with any of the implementation details. So Docker sends back, OK, here's your container ID. Then we say, open these standard I/O streams on that container. Docker says, super duper, here's your file streams. And from this point on, we communicate with the process over those file streams. So on the standard in, we tell it to execute this program. And here's some arguments. Behind the scenes, this builds up some environment variables and actually runs another process inside the container. And our little driver program says, yep. And then it comes back a little bit later with some command output. If the command threw an error, it would write that back on standard error and send along an exit code and that kind of stuff. After it's all done, we say, all right, tear down the container, we're done. And the container gets destroyed. This whole dance takes just a few hundred milliseconds. And I'll dive into some of these numbers here in a minute. But for what is, depending on your use case, potentially kind of expensive conversation to have, 200-300 milliseconds is not exactly like blazing fast. We get a lot, we are able to offload a lot of these concerns directly onto Docker, which is quite nice. So let's talk about performance. Container creation takes about 200 milliseconds, and I'll dig into this a little bit more in a minute. Process execution overhead, there's practically none. It's lost in the noise. It's like a millisecond or two at most. And container destruction takes about 90 milliseconds. Now, that said, container creation, which is the blue line here, has this really sad exponential behavior under load. And that makes me suspect that there's some sort of locking going on inside the Docker daemon. So along the bottom here is a number of concurrent processes asking Docker to create containers. So we go from 1 to 2 to 4 to 8. And this is the number of milliseconds that it takes for the container to get created. So to, for sure, create has this wicked exponential curve going on. Destroys a little bit better. Takes a little bit longer before it really starts ramping up. But the I/O, so where we're writing and reading from these input and output streams, and on the other end where it's shelling out and creating processes, is like just completely, not really of any real impact at all. So this has some practical implications, right? So you've got poor container startup scalability. Our initial swing at implementing this, since this aspect of the product is written in Go, we would just start up Go routines and just say, here, there's the API, go nuts. Well, that clearly was, thundering herd effect set in rather soon, and so that was clearly not going to work for us. And so what we try to do is cache and reuse containers wherever we can. So this is really the motivation for writing our own driver, is that since we're talking to the driver, we can tell it, hey, just hang out. I'm going to get back to you in a minute with some more work to run. And the driver knows that if we don't, to tear itself down and clean up the container. The I/O API, the part where we talk to standard out, standard in, standard error, once you get it working, super straightforward. Unfortunately, like most open source projects, the documentation is incredibly lacking. This whole thing, start to finish, the first time we implemented it, took about a week, and I would say 2.5 days was spent just on this point right here. So the pros, though, so low documentation and a really low user education effort. Most people know Docker or want to know Docker, and so you can capitalize on that. If you tell people, package your code up as a Docker image, and we'll take it from there, they love it. So it has a defined image format with good tooling. When we originally tried doing this plugin API, the very, very first one, we tried defining our own tarball directory structure and was just awful. Secure process execution, and the Docker repos as discovery mechanism. This is huge and something people don't think about enough. Being able to browse Docker repos and do searches and find interesting things to look at, I mean, it's a big reason why GitHub is so popular. So I'm getting the sign that I'm almost out of time. That's it for what I had to talk about. Do I have time for any questions?
You actually do not.
Okay. No, that's fine.